Good day everyone. In today's lecture, we'll be discussing about the switching characteristics of an SCR, which has the turn on characteristics of an SCR, which comprises of the delay time, the rise time and the spread time. Then we'll be discussing about the turn off characteristics of an SCR, which comprises of the reverse recovery time and the gate recovery time. Also, we'll be discussing about the circuit turn off time. We will be discussing about the switching characteristics of an SCR. Now for discussing about the switching characteristics of an SCR, there are two modes in which an SCR works. One is turn on and the other is turn off. Now we will be discussing about what all different modes are there in turn on and also what all different modes are there in turn off. Now basically talking about the switching characteristics, let us start with the thyristor turn on characteristics. Now thyristor turn on is nothing but the transition time that is taken from a forward off state to the forward on state. Now for example, the thyristor is initially off. Now from this off, it will not suddenly turn on. For turning on, it will take some time to reach the on state. Now what all gaps or what all periods is occurring in between this, we'll be discussing about that. This transition, that is the transition time from off state to on state. During that period, what all things are occurring, that we'll be discussing about in this we'll be discussing about now. Before discussing about that, this is the switching characteristics curve of a SCR. Now here we can see the first quantity is nothing but the voltage, what gate pulse voltage we are giving. The second graph we can see it is having VA and it is having IG. Two quantities are plotted in the same graph. Then we have the third graph that shows IA, the anode current, and the what all power losses or what all power losses are there, that is showed in the fourth graph. So we'll be discussing about these two. We'll be discussing these two graphs. We'll be discussing for finding out what are all the different time periods in the on and the off process. Now talking about the thyristor on process, turn on time has three parameters, that is delay time, rise time and spread time. Now these three together, it forms the thyristor's turn on time. Now let us discuss about the first, that is delay time. TD, it is called as the delay time. Delay time is nothing but when the anode voltage falls from VA to 0.9 VA. Now this is my anode voltage. My anode voltage is 100% here. Now it is trying to fall. Now when it is reaching 0.9, that is 90% of its initial value, the duration in between that is the duration in between anode's 100% value to 90% value is called as my delay time. Delay time is nothing but anode's voltage from 100% to 90%. The time period that is taking to reach from 100% to 90% is called as my delay time, or delay time can also be termed as when the gate current is 90% value to 100% value. The time duration in which the gate current is reaching from 90% value to its 100% value, that can also be called as my delay time, or delay time can also be defined as from forward leakage current to 0.1, that is 10% of the anode current's value. This is the final value of my anode current. I'm not talking about the final value. 10% of the initial 10% of the anode current's value from forward leakage current. This is my forward leakage current. From forward leakage current to 10%, the duration which is required to reach this value is called as my delay time. Now in delay time, the anode current will start flowing in a narrow region. Now let us look here. Now for example, I am having three junctions J1, J2, J3. J1 and J3 are forward bias, so there is no problem here. We'll only be discussing about junction J2. Now let us consider this is the cross section of my SCR of junction J2. Now during this junction J2, what is happening? The current flow, like in a dam, for example, if I am having a dam's wall, now for example, if this wall has to rupture, it has to start from some one point. From this point water will start gushing out, then slowly this will rupture the other parts, then the whole dam structure will be collapsed. In that similar manner, here also we can see that this is the full cross section of my SCR's junction J2. Now for making the current to flow, it has to start from some small region. Now this region is where the current flow initially begins. Now here we can see that at this point the gate current's density is the highest, and because of that gate current will start flowing from this point. Now this is the first, or this is the operation in TD. In TD, gate current will start flowing from a small portion. Now the value of TD will be in microseconds. It will be some fraction of microseconds. The length of the time period for delayed time will be in a fraction of microseconds. Now we are having the second, that is my rise time. Now in rise time, what will happen is, now the anode current will rise from its 0.1 value to its 0.9, that is from 10% value of my anode current to 90% value. The time that is required to reach here, we call it as the rise time, or rise time can be said as the portion where the anode voltage from its 90% value, it drops to its 10% value. Now the gap in between these two instants are called as my rise time. Now during rise time, we can see that the value of IA is also high, the value of VA is also high. So in this portion we have larger power losses we are having. Now as we are having larger power losses, there are more chances of local hotspots being formed. Hotspots means, now for initially during delay time, current was flowing only from a small region. During rise time, the current's flow is trying to establish itself, so it is some current is trying to flow from a larger area. Now when the area is increased at this portion, for this small portion, that is for the entire duration, for the entire period, for the entire area, if I had 100 watt of power flowing, and for this small area if I am having 100 watts of power flowing, where will be the temperature rise more? The temperature rise will be more in the second case. Now this is what is happening here. Now as we have seen in the graph, the value of VA and the value of IA are high, that is VA IA power losses will be high in this second, that is in rise time it will be high, and there are chances of local hotspots being formed, and because of this junction J2 can be damaged permanently. Then we have the third, that is called as my spread time. Spread time is nothing but when the anode current rises from 90% of its value to its 100% value. Now this gap is called as my spread time. Now in spread time we can see that the anode current initial value was 90, but it has reached its 100% value. The load current value has been established. Now here we can see one more thing, that the anode voltage, it is going to some on state voltage drop, that is it is going for some leakage that is occurring across the SCR. Now this duration is called as my spread time. Now in spread time, what will happen is the conduction will spread across it will spread uniformly across the junction J2. This is for spread time, this is for rise time, and this is for delay time. Now in spread time, the current will start flowing uniformly across the entire cross section. Now here we can see that the turn on time is nothing but it is the sum of delay time, rise time, and spread time. Now we can see that this whole duration, that is the on time, is around 1 to 4 microseconds. This full on operation, it will happen in 1 to 4 microseconds. Now we can see here that the higher the magnitude of the gate current, the lower will be the value of turn on time. If I am giving high values of IG, I will get my T on time to be low, because this current spread will happen faster. Now if we are hard firing a thyristor. Hard firing the thyristor means we are giving the value of Ig some several times more than the minimum gate value required. For example, the minimum gate value required is, for example, some 5 amperes. Now I know that only 5 ampere has to be given, but what I'll do is I'll start giving 25 amperes. Now when I'm giving more amount of gate currents, now that is called as hard firing my thyristor. Now we know that the forward leakage current is now, for example, if I have to classify the 3 sections, that is my delay time, my spread time, and my rise time and my spread time, I can say that from forward leakage current to 0.1 ampere, it is called as my delay time. From 0.1 IA to 0.9 IA, that is my rise time, 0.1 IA. Then from 0.9 IA to IA, the duration that I am reaching, I call it as my spread time. Now easily we can remember that the on time, it has 3 durations, that is delay time, rise time, spread time. Delay time is nothing but from forward leakage current to 10% of my anode current. Then 10% to 90% is my rise time, 90% to 100% is my spread time. Now we will start discussing about turn off time of a SCR, that is the turn off characteristics of an SCR. The turn off characteristics is nothing but the SCR was initially conducting, and from conduction directly it will not come to off state. For coming to off state, it will take some time. So the transition that a SCR is making when it was already in conduction state, from that state to its off state, we call it as the thyristor turn off time. Now this in here we can say that the SCR is coming to the blocking state, or we can also call this to be the commutation process, that is the duration from on to off. This happening, we'll be calling it as the commutation process. Now to understand the commutation process better, let me sketch a small diagram. Initially we know that this is my thyristor PN. Now the anode is connected to plus, the cathode is connected to minus. Now initially what is happening, the thyristor is not turned on. Now when the thyristor is not turned on, through all the layers we have uniform distribution of the charge carriers. Now when I am applying biasing, that is at the end of my on state, we can see that as here it is a plus charge is there, all the holes will be repelled, all the holes will come to this border. As here a negative charge is there, all the electrons will be repelled and it will come to this border. Then we can see that to the P region, negative, and negative is given to the P region. Now because of that, all the holes from the P region will be attracted here. As all the holes are attracted here, electrons will get accumulated here. Here also similarly we can see that this is happening. Now if you remember the PN junction diode, we can say that this is my forward biased, this is my reverse biased, and this is my forward biased. Now here we can see that this a depletion layer is formed. So here we can see that when my thyristor was on, there was redistribution of charge carriers. That is initially when we were discussing initially all the layers PN, there was uniform charge distribution. Now after the turn on process, what is happening is this is the state in which my SCR will be there. Now I have to return my SCR to the previous state, that is to the previous state where all the charges are equally distributed. Now why this is important? Because if I do not bring my SCR to the previous state, what will happen is, now what I am doing is I am reverse biasing this. Now what I will do is I am making this to be minus and I am making this to be plus, and gate current is removed, but the charges are not completely redistributed. That is, for the charges to come to its initial state or to change its position, some time is required. And during this duration, what I do is again I change the biasing, that is I make it to be plus and minus as the initial, again my thyristor will start conducting. That is, there will be a flow of current in my thyristor without the gate current being applied. So to overcome this, I have to take my thyristor to the previous state. That is, if the forward voltage is applied at the moment anode current falls to 0, and even if no gate is applied, the device will turn on suddenly. That is, to avoid this in a thyristor, it has to be reverse biased, and the reverse bias has to be given for some certain amount of time. That is, all the recombination and all will occur, and the anode current value will become to 0. Now, talking about the turn off time, in turn off time we have two things we have. One is reverse recombination, reverse recovery time, and the other is my gate recovery time. Now let us discuss what is reverse recovery. Reverse recovery, I term it to be TRR. Now during TRR, what will happen is the current, that is the anode current, will start to build in the reverse direction. Now what happen is, VAK, it was initially forward biased. I am removing this forward bias. Now when I am removing this forward bias, already my charge carrier have assumed some positions. Now that position, it has to come back. Now when it is coming back, a reverse current is that is, current will flow in the reverse direction. Why there is a current flow in the reverse direction? A current builds in the reverse direction because of the presence of charge carriers in the 4 layers. Now we can see that the reverse recovery current, that is J1, J2 and J3, these are the outer junctions. As these outer junctions are directly connected to the terminals, or directly voltage is made available first in J1 and J3. Because of that, we can see that the reverse recovery current, it removes the excess carriers from junctions J1 and J2. That is, junction J1 and J2 recombination occurs first. Now here we can see that is from time duration T1 to T2, what is happening? Whatever reverse current is flowing, the reverse current is flowing because of the change in direction of anode current. Now J1 and J3, all the recombinations has been done. After this, almost all the charge carriers have reached to their initial position. Now only some charge carriers are remaining, which has to come back to its previous position. Now after T2, this is the T2 duration. After T2 duration, the charge density decreases. Why it decreases? Because major portion have rushed off to their previous position. Now only some charge carriers are remaining. Therefore, here also you can see that the direction of current is reverse, but its density has decreased. Now that is below the time axis, it is my negative current. Now here we can see that from T1 to T2 it is rapidly increasing, but after T2 the current is staying reverse, but its density has decreased. Now we can, this T1 to T3 duration, I call it as my reverse recovery time. Now during reverse recovery time, whatever charge carriers were there across J1 and J3, all have gone to their initial position. Now we come to the gate recovery time. Gate recovery time I am achieving in between T3 and T4. Now here we can see that in gate recovery time, the junction J2, it has some strapped charges. Why I am calling it as strapped charges? Because it is not directly, junction J2 is not directly connected to the biasing. Therefore, some trapped charges are there. Now these trapped charges will decay by recombination only. That is, it is only possible if I am applying the reverse voltage for some duration of time. Now if I am applying the reverse voltage for some duration of time, it will recombine on its own. Now we can see that the turn off time TQ is the sum of reverse recovery time plus gate recovery time. Now this TQ time, it will be of the duration 300 to 100 microseconds. Now moving further, we can see that the turn off time, it depends on two factors. It depends on the magnitude of forward current. Now if plus IA, that is when it was on, if plus IA, if the value of plus IA was a higher value, then more amount of trap charges will be there. If the the anode current's value was less amount of trap charges will be there. So the turn off time will directly depend on the amount of forward current that was applied, and it will also depend on the amount of reverse voltage that is applied. If the amount of reverse voltage applied is greater, the turn off time will be less. If the amount of reverse voltage applied is lower, the amount of turn off time will increase. Now looking at this diagram, we can see that we also have one more duration, that is T5. That is, we have discussed from T1 to T3, T1 to T4. From T1 to T3 it was for junction J1 and J3. From T3 to T4 it was for junction J2. Now here from T4 to T5 also we have a small duration. Now that duration, that is from T1 to T5, we call it to be TC. TC is nothing but the circuit turn off time. Circuit turn off time is calculated for practical circuits. That is, if an in the instant when an anode current reaches 0 to the instant reverse voltage due to the practical circuit reaches 0. That is, the practical components that are connected, that will also play some role in the turn off of the SCR. Now if the circuit that is connected, that circuit also allows the SCR to completely recombine. That is what is shown by TC. The value of TC should be greater than the value of TQ, because if the value of TC is not higher, the device may turn on undesirably, and this process will be calling it as commutation failure. Commutation failure means what? The device is completely not turned on. Even before the device is completely turned off, if I give a pulse, my SCR will directly turn on. That is, it will not have to go through all the hassles of rise time, delay time and spread time. So to overcome that, the circuit turn off time should be greater than the device turn off time. Now depending on the turn off times, I can classify my SCRs. That is, if the turn off time of my SCR is in between 50 microseconds to 100 microseconds, I'll be calling it as slow turn off, and this type of thyristors are called as converter grade thyristors. Now converter grade thyristors are cheaper. It can be used for rectifier circuits, for cycloconverter circuits, for AC voltage controller circuits. Wherever the AC supply I am using, in that cases I can use this slow turn off thyristors can be used, or converter grade thyristors can be used. Now next classification that I have is fast turn off thyristors. Now fast turn off thyristors, the value, its turn off value will be in between 30 microseconds to 50 microseconds. Now these are called as my inverter grade SCRs. Now inverter grade SCRs are comparatively its value is it will be of a little more value. Its cost is more. Now these type of circuits will be used where the input is DC. That is for inverters, for choppers, for forced commutated converters. In that type of circuits I can use this inverter grade SCRs.